last year. And I appreciate your attendance. And I would like to mention that my first PhD student, Chris Hill, is joining us. I also have 2 colleagues joining us from China as well. I invite them.
Just one thing I want to ask you before you start. I started recording. I hope you don't mind that I record.
Oh, I don't mind. Go ahead.
Okay. Yeah, that's
good.
It. Thank you.
All right. So the title of my talk is Some Results on Products of Exponentials. So this is a joint work with my 2 PhD students. They already graduate. Elaine is now a postdoc at UNR, and Roy Liu is an associate professor at North Greenville University. All right, so let's move on. So as I said, I want to introduce them. So, why doesn't move? Okay, next one. Okay, this is Roy Liu, the left one. The right one is Elaine. All right. So let me introduce some notations. So let's start with Cn by n. Cn by n is the usual notation for the vector space of all n by n complex matrices. However, sometimes I would like to use another notation to denote the same set. This is GLNC right here. The German GLNC denote the same set. However, it has, or I should say, I emphasize the algebraic operation here. Whenever I use GLNC, that is the bracket operation, the Lie bracket. This is well known. That is the bracket of AB is AB minus BA, where A and B are n by n complex matrices. All right. Associated with the German GL, there is a group called the general linear group, which is the set of all n by n non-singular matrices. All right, so I think we are all familiar with that. The next set I'm going to talk about is ONC, which is the complex orthogonal group. If you're not familiar with this group, don't worry about that. I will give you a definition later. ONC is a subgroup of GLNC. All right. HN is the notation for the set of all n by n Hermitian matrices. Hermitian means A star is A, where star is the complex conjugate transpose. PN is the space of all n by n positive definite matrices. Well, a positive definite matrix, well, it could have many definitions, but one definition is it is a Hermitian matrix and all the eigenvalues are positive. All right. And UN is the group of all n by n unitary matrices. And ON is the group of n by n orthogonal matrices. Whenever we say orthogonal, it means real orthogonal, right? And as you saw a moment ago, we have the complex version, ONC, the complex orthogonal group. So this guy is the real orthogonal group. I would like to mention that this is non-compact. ON is compact, UN is compact, this is non-compact as a group, right? GLNC as a group is non-compact as well. So let's move on. Matrix exponential. Well, we're all familiar with this notion. Suppose you start with a complex matrix X, n by n, and then you take the exponential of that matrix. So this is another notation for the exponential. Either I use e to x or exp of x, which is an infinite series. So you can see that. Oh, so this is the series. There's I plus x squared over 2 factorial plus x cubed over 3 factorial and so forth and so on. So this is a series. Well, matrix exponential can be used to solve system of linear ordinary differential equation, that is ODE. As a matter of fact, Lie group evolved many years ago, more than 100 years ago, from studying differential equation by Lee. Okay, this is the classic example. Given a matrix A, n by n, real, and xt is a vector, column vector in Rn, and x0 is the initial vector, also in Rn, where t is a parameter. You can imagine that this is the time t, and then you take the derivative, all right, of that, and it is a times xt. So this is the given differential equation. We call it the system of linear ordinary differential equations. And x at the point 0 is x0. Well, what is the solution? The solution is well known. Here is the solution. So x of t is the exponential of ta times x0. All right, remember this guy is an n by n matrix, and x0 is a column vector of length n. So as you multiply them together, everybody is in Rn. So this one is in Rn, this one is also in Rn. You can replace Rn by Cn or Rn by n by Cn by n. It makes no difference. Okay, here's a list of properties of matrix of exponential. First, I would like to mention that if you choose a matrix G very close to the identity, all right, in GLNC, the group, then such G can be expressed as the exponential of some matrix X in Cn by n, or you can use the German GLNC to denote that. So in other words, within a small neighborhood at the identity, you have some sort of diffeomorphism in between, local diffeomorphism, I should say, between the uppercase GL and the German GL. All right, these are nice properties for the exponential matrix exponential. Determinant of EX is E to trace X. All right, and if you take the transpose of X and then you take the exponential, it's exactly the same. You take the exponential first and then you take the transpose. So that's the second one. And the same thing also is true for the complex conjugate transpose. And we have nice property regarding similarity. Say, for example, if you take S inverse, that is the conjugate of EX, all right, then you get that. So you can raise it to the exponent here. Okay. Another nice property is if X and Y commute, that is XY is YX, or the Lie bracket of X and Y is 0, then what happened? Well, the product of EX and EY is exactly exponential of X plus Y. Is this true even X and Y not commute? Well, thing is this. If they don't commute, then you don't have the equality. So if XY is not YX, then in general, you don't have the equality here. When n is bigger than or equal to 2, of course, right? Because if n is 1, then you have the scalar case. So far, any question? Feel free to ask me. If you have any question, I would be happy to answer it. And don't be afraid to interrupt me. Feel free to do so. I don't see any questions, so let's move on. All right, so let's talk about the exponential map for the general linear group. Well, this exponential map, all right, from the German GL to the group GL or the uppercase GL is surjective. Well, how to see it? Well, you can use Jordan canonical form to do it and couple with this property. That at first you convert X into its Jordan canonical form, and because of that, and then you start to work with each Jordan block. and then you build up the theory. So this is surjective. However, this is not injective. Okay, let's see an example. If n is 2, so we are talking about 2 by 2. Oh, sorry. We are talking about 2 by 2 matrices. Of course, if you take the 0 2 by 2 matrix, the exponential of the 0 matrix is the identity matrix. No question about that. However, let's consider another matrix right here. This is another matrix. 0 minus 1, 1, 0. This is our J. And if you take the exponential of 2 pi j, you get also the 2 by 2 identity matrix. And of course, 0 and 2 by j are not the same, but they have the same image. All right, the same image is the identity matrix. So this is not surjective. Well, what happened if you replace the field C by R? What would happen? Well, let's consider the real exponential map. Right now, the underlying field is R, okay? And this is the corresponding Lie algebra. This is not even surjective. That is, you can find something on the right-hand side here, and you cannot find a P image, all right, on the left side. Well, how to do that? Well, this is the matrix we're going to pick. Minus 1, 0, 0, minus 2, which is non-singular because the determinant is 2. So it's here. Everything is real, right? Well, can we find a matrix X in the Lie algebra such that EX is this matrix, minus 1, 0, 0, minus 2? The answer is no. Well, suppose you could find such a matrix X. Well, X would have eigenvalue, let's say alpha and beta. All right. If alpha and beta are eigenvalues of X, then the eigenvalues of EX must be e to alpha and e to beta, right? But EX is this matrix, and it's a diagonal matrix, so the eigenvalues must be minus 1 and minus 2. All right? So alpha and beta must be non-real complex numbers, right? But don't forget, X is a real matrix. So alpha and beta must be complex conjugate. If they are complex conjugate, then these two moduli must be the same. There's no way, because look at that. This is minus 1 and minus 2. How come they have the same moduli? So this is a contradiction, right? So this is not surjective. All right.
And it is neither injective, right?
What's your question?
I mean that the real exponential map is not injective either, right?
No, this is not surjective.
Yeah, and not injective too, right?
Oh, yeah, I didn't mention that. Yeah, I believe this is true too. All right, so the next slide is to show a very famous formula, Baker-Campbell-Hausdorff formula. EX-EY is EZ, right? Where Z is in this form. I mean, there is a pattern, but the pattern is complicated in terms of an infinite series and a bunch of brackets, actually infinite number of brackets here. Right, so you can see that the exponential of, the product of EX and EY is exponential of something, let's say Z. But what is Z? Z is X plus Y. And then you can imagine that the rest is just garbage or the tail part. But you just cannot dump it away, all right, because it exists there, all right? But anyway, it's related to XY, all right? Well, this is natural because EX is from EX, EY, so there must be some relation involved. And this is the nice relation. However, this is not very practical. Now, in general, all right, as we already mentioned, EX, EY, and E to X plus Y are not the same. And then we ask the next question. Okay, given that X and Y are n by n complex matrices, can we say the following? And then you may say, oh, what do you mean by U, V? Let's say U and V are non-singular matrices. Say, for example, can we find non-singular matrices U and V such that EX, EY would be the right-hand side? This is the right-hand side. All right, for some U and V. Well, the answer is no. Well, let's consider this. This map from the Hermitian matrices to the set of all positive definite matrices is a diffeomorphism. Since it's a diffeomorphism, it's a bijection. Okay, what is P squared? Right, P squared is a notation. It's the collection of all products of, A and B. A and B are in Pn. So it's a product of AB, where A and B are in Pn. Now this is, if you work it out, turns out this is a set of all diagonalizable matrices with positive eigenvalues. So Pn, right, is obviously here because you can choose B as an identity matrix because identity matrix is positive definite. So it's there, but not exactly the same. Right, so this is bigger. This set is bigger than this set. All right. Now, I want to mention that once I have this, I can pick X and Y in Hn such that Ex now in Pn and Ey now in Pn. I take the product, which is here. All right. That is in Pn squared, but not in Pn. Notice that this guy, all right, is in Pn squared. However, you can see that this is not in Pn. All right. Suppose you pick unitary matrices, U and V. All right. So it doesn't work that way. That's not true in general. Now, I'm going to introduce some work of Wasson and Robert C. Thompson. I call him Bob Thompson. He already passed away in the late 90s. Okay. And Wasson is a former PhD student of Bob. He is now an associate professor at San Jose State University. Not too far away from him, maybe about 4 or 5 hour driving distance. And the second photo is Bob and me that we took at Bradford University in England back in 1988, right? Quite a while, more than 30 years. So let's mention Thompson's work. Oh, did I mention Wasson is a former student of Bob? I think I did. Okay, it's uses and the problem. Thompson's exponential formula for UN. UN is the unitary group. Now the exponential map here. We have the group UN. This is the set of all skew Hermitian matrices because Hn is the set of all Hermitian matrices. So you multiply it by I, which is the purely imaginary number, square root of -1. This exponential map would send skew Hermitian matrices to unitary matrices. All right. Okay. And back in 1986, Bob Thompson proved the following theorem. Okay. All right. I should say not proof, but conjecture. All right. Mentioned this conjecture in a 1980 Auburn Matrix Theory Conference. So in 1980. And then he proved it in 1986. But the proof relies on an announcement, right, of someone, and is a Russian mathematician that I would mention. Here's the theorem. So you start with A and B, Hermitian matrices. So you have EIA, EIB. Both are unitary matrices because IA is skew Hermitian, IB is skew Hermitian. And as you know, unitary matrices form a group. So EIA times EIB would be unitary. All right. And it turns out Thomson managed to prove that you can find U and V both unitary, such that the left side and the right side are the same. So let's try to understand the formula. Okay. Here's the formula. As I said, EIA, EIB, both are unitary matrices. So as you multiply them together, you get a unitary matrix. But what is the form of the unitary matrix? And of course, you can say, oh, we have a Campbell-Hausdorff-Baker's theorem, okay, or formula, and then use it. But you know, as I mentioned, go back here. Not very useful because you have this infinite series, right? So not much you can tell. But now you can see this is UA U inverse. So you can imagine that first A is a Hermitian matrix. U is a unitary matrix. So this is a conjugation, right? So, or similarity. So you have UA U inverse here. How to interpret that? You can imagine that the unitary group acts on HN. So this is the unitary group, acts on HN through conjugation, or this is the conjugation, UU inverse. So UA U inverse can be interpreted as an element of the orbit, all right, of the matrix A under the action of the unitary group. That's how I interpret it. So similarly, this guy is an element in the orbit of U under the unitary group action through conjugation or through similarity, if you like, using the matrix language. All right. So this is nice. All right. That is, you can find, but Bob Thomson's theorem doesn't tell you how to find U and how to find V. So this is a theoretical result, though it's beautiful. Well, as I mentioned, Thomson's proof made use of a very nice result announced by Lipsky for the eigenvalues of the sum of Hermitian matrices. However, in his very short paper, maybe 1 or 2 pages, there was no proof in this Russian's mathematical paper. Lipsky is a famous mathematician, but seems like more than 30, 40 years ago, they like to publish announcement without too much detail. And Bob also used a theorem in the area of perturbation theory, all right, in order to finish his proof. But at that time, the proof of Lipsky was not given, okay? So it was a little bit skeptical, but later it turns out Lipsky's announcement or claim is true, but it requires very deep proof from other people. So I just want to mention that. So anyway, Thomson's result is true. This is a picture of Lipsky. He passed away more than 10 years ago. A famous guy in operator theory. All right. Okay, then let me talk about polar decomposition. All right. So this is polar decomposition, just undergraduate stuff. So you can represent a complex number by using polar decomposition. Either you can do it this way or you can do it this way. Uniqueness doesn't exist for C at the origin. Everybody knows that. However, uniqueness exists for, all right, non-zero complex number. That is our GL1C. All right, then we have polar decomposition for high dimensional GL and C, all right, which is now we call it the matrix polar decomposition. So it means each matrix in in GLNC can be expressed as product of a positive definite matrix and a unitary matrix. So this is the way to write it. Someone would like to express it in the context of singular value decomposition, which is fine, because if you further decompose this P by using spectral decomposition, you get singular value decomposition. But one thing I would like to mention is many people working on matrix theory don't know about that. That is, polar decomposition, as a matter of fact, is a diffeomorphism in the following sense. So you factorize, or you break the GL into two pieces. One is HN, another one is UN. And so this is an order pair. X is from HN and U is from UN, and then you take the product. So this is a diffeomorphism. All right. Now GL is pretty mysterious to understand, at least the topology. But you can see GL and C can be reduced to, at least topologically, reduced to the study of HN and UN. Of course, there is a very important operation, that is the multiplication. HN, as a matter of fact, is a vector space. All right, UN is a compact group because it's unitary group. Right, so diffeomorphism. Since it's a diffeomorphism, it is a homeomorphism. So that's why I said topologically, GLNC can be reduced to the study of HN and UN. But don't get me wrong, there is a multiplication. Multiplication is also mysterious. Thomson 1986 results handles the product of two elements in UN, namely unitary matrices. So you have that. So I just reiterate the formula here. Next. This is the picture. I try to visualize it. So you have the exponential map from HN to PN, and this is it. And you can imagine this is the situation. I don't know whether you are interested in soccer game. Here we have a soccer ball. All right. So if you flatten the soccer ball, and then you get this picture. So the exponential map is kind of from this flat space to the curved space. So that's why we have that. So this is the set of all positive definite matrices. This is the set of all Hermitian matrices. All right, so let's move on to another topic, that is the symmetric space. And we have a quotient space here. All right, there's quotient space here. And why we mention the quotient space? Because the polar decomposition, look at that. Because GL is P times U. All right, so if you mod the left side by UN, you expect to get PN, right? Yes. So you get that. So you have a projection, right? And this is the natural projection, right? And you can identify PN with this quotient space, all right? And this guy that I highlight is called a symmetric space. And this is the projection. G, it will send to the coset, G dot UN. And this natural projection enables the identification HN and the tangent space at the origin of this symmetric space or the quotient space. All right, and you can write out this is identification. As a matter of fact, this is a G invariant Riemannian metric, and the metric is well known. I don't think I have it here. All right, so. All right. And this Riemannian metric is invariant under the natural action of GL on this quotient space. And you may say, oh, what is the action? This is the action. So you have a group G element. So it's from here. And it acts on this guy. How to act on it? Well, just translation. So it's through the left multiplication. You just multiply X by G, and then you get that. Okay. But what is the effect of this action on PN under the identification? All right, and it's given here. All right, so let's try to explain it. Let's start with the complex conjugate transpose. it is a diffeomorphism. So you have that, all right? So you have this map. This is surjective. So GLNC to PN is surjective. So you just you map it to GG star. And then you identify these two guys. All right, so you identify these two guys, and then the coset is mapped to GG star. All right, and this is bijective. All right, now G may not be unique here, right, inside the coset because it's just a representative. But somehow, as you multiply them together, you get the same GG star. All right, and so this is the action. So in other words, concurrence or star concurrence can be interpreted as the action of GLNC, all right, on PN. And of course, PN acts on itself through concurrence as well. So if you replace GLNC by this PN, all right, you can do the concurrence as well. Now, let's talk about the first exponential conjecture of So and Thomson. All right, so let's look at this. When we talk about EX, EY, but if X is Hermitian and Y is Hermitian, then EX, EY won't be in PN, the set of all positive definite matrices. But how about this? If you chop your EX to half and move it to the right-hand side, you get that. You don't change its spectrum, right? Because of similarity. They have the same spectrum. So you get that. It is in PN. So it must be exponential of Z because the exponential map on HN to PN is a bijection, right? So what can we say about Z? All right. So they have the first conjecture. The first conjecture is this. Okay, given X, Y in HN, there exists unitary matrices U and V such that the left side is the right side. So in other words, the right side can be interpreted as exponential of something. And that something is UX U inverse plus VY V inverse. And UX U inverse plus VY V inverse can be interpreted as the sum of two elements in the orbits of X and Y under the action of the unitary group through conjugation. It's a long statement. But anyway, this is how to interpret the formula. All right, so this guy, as I said, is in PN. This guy is also in PN. But as you read the paper of So and Thomson, there is no way you can tell how to construct U and V. All right, so I would like to mention that. So first conjecture. Some remark it is obvious the conjecture is true if X and Y commute. All right, so because you can move things around, so you can move this to the middle and then combine with the second half of EX over 2, and then you get that. All right, so in that case, U and V are the identity matrix. On the other hand, if X and Y don't commute, then you don't have that for any unitary matrix W. Right. In fact, if you take the trace, you get that, and then you get that as well. Let's just mention this remark. Well, Bob Thomson passed away, I believe, in 1997 or 1998. I don't remember exactly. Oh, no, sorry, 1995. I said it here, okay, in 1995. So as they published their paper in 1991, all right, at that time it was a conjecture. And then Bob passed away several years later. And then about 10 years later, maybe 9 years later, So established the first conjecture. It turns out that it is true, the first conjecture. And So used a very deep resolve of Kayoko, all right, in order to do that. And Kayoko's result came out after the death of Bob Thomson. So that's why at that time, Bob couldn't use the result to do it, right? And this is Kayoko's theorem, all right? So this kind of a dictionary translation between the Hermitian case and the positive definite case. So you start with alpha, beta, gamma in Rn in descending order. That is, the entries of each vectors each vector are arranged in descending order. Then the following statements are equivalent. There exists xy in Hn with lambda. Lambda is this eigenvalue, okay? Eigenvalues of x is alpha, eigenvalues of y is beta, and eigenvalue of x plus y is gamma. And this is the famous sum of Hermitian matrices. And Kayoko was the first one to prove that. And then now he established that. Another one, that is, you can do the same thing for positive definite matrices, and these two are the same. All right, these two statements are the same. All right, here is the Lie setting. Let me see how much time I have. I don't have much time. So the Lie setting is, let me go real quick. You start with a non-compact, connect the semi-simple Lie group with Lie algebra G, and you have the Cardan involution. And associated with this Cardan involution, you have the fixed point set, and you have the differential of theta. We also call it theta, but it's a smaller theta. And then associated with this this theta, you have the Cardan decomposition on the algebra level, so that you have the German K and German P, and this is a direct sum. And associated with the Lie algebra, you have the Killing form B, and the Killing form B is negative definite on the German K and positive definite on the German P. And then you can turn the Killing form into an inner product through this trick. And then we have the so-called Cardan decomposition. So the prototype of Cardan decomposition is the matrix polar decomposition. So if you use, say, for example, G is SLNC, then you get the regular polar decomposition. And then you may ask me why you don't use GL and C, because GL is not semi-simple, right? So you have similar setting. You have the symmetric space. You have G mod K, and then you have the natural projection, and then you can identify the quotient space with the big P, and so forth and so on. And you also have the action. The action is through translation, left translation. And then you also have G star, but now star is no longer the convex conjugate transpose. Star is defined in this way using inverse and the group level Cardan involution to do it. And you have the action, all right, which is GG star, all right. So, here's the action. Action is C, all right, star concurrence. Once we have all this abstract setting, I managed to extend with Roy and Elaine in the context of the symmetric space. So you can see I start with X and Y in P, the exists U and V in K, all right, such that this is exactly that for some U and V. And here the conjugation is replaced by the big adjoint, all right? So, and the key idea is to use a very nice result of this paper, the second paper, all right? Our results are published in 2021 in Linear Algebra and its Applications. All right, so let me illustrate why our result is good. All right, so this is the general result. So suppose you talk about GL and R, then you have that. So you start with two real symmetric matrices X and Y. There exist orthogonal matrices UV in SON, such that you have this. All right, and then you may say, can we use ON? Sure, because ON is bigger than SON. All right, but anyway, you can find SON to do it. All right, the transpose. All right, so what you can do is to apply our result to SLNR, and then you can get the so-called the Cardan decomposition, and then apply the result here, and then you get that. Well, then you may say, what happened if trace X and trace Y are not zero? Because I didn't mention that this P, I did a zero trace, right? But then you may say, oh, what happened if X and Y have non-zero trace? Don't worry, it works. It's just a little trick, so you can decompose your X and Y that way, and then through multiple, all sort of operation or algebra, you get that. So the difference is a center, so it can be handled. Okay, ON, the complex orthogonal group. I promised that I will give you the definition of this complex orthogonal group. This is the definition. ON is the collection of all non-singular complex matrices such that Q transpose Q is the identity matrix. Now this looks very, very similar to ON, but it is much bigger than ON because it allows complex numbers here, all right? And it has two connected components. The identity component is this one, all right? Okay, all right. And as a matter of fact, SON is in SONC in ONC, all right? Now, polar decomposition of ONC and SONC, do we have that? Yes, we do, because you can get it from Cardan decomposition. Each complex orthogonal matrix Q can be decomposed in this form. Q is R times EIK, where R is in ON and K is in Rn by N. Not only that, K transpose is minus K. That is, it is a skew symmetric matrix. What happens if Q is in SONC? That is the identity component of the complex orthogonal group. Then you can choose R in the SON. So you can restrict your selection. It's right here, SON. If determinant of R is 1 and determinant of EIK is 1, all right, so we have that. Then these two guys are also here. So I just demonstrate the polar decomposition of complex orthogonal group and the special complex orthogonal group. Well, product of exponentials associated with ONC. Again, using our theorem, we can get this. So if you have two real skew symmetric matrices X and Y, I claim there exist special orthogonal matrices U and V such that this formula is true. Again, you just pick the right Lie group, which is here is SONC, and then you decompose it according to the Cardan decomposition, and then you can get this one. All right, so I think our result is a powerful result. Second, we would like to talk about the second conjecture of So and Thompson. I have a conversation with Watson So late last year, I believe maybe in December last year. And I asked him whether the conjecture is still open, and he told me, yes, it is still open. He would like to see it being solved. All right, so back in 1991, So and Thompson mentioned two conjectures. They solved the first one, and the second one is still unsolved. So let's take a look at the conjecture. Let S and T be n by n complex symmetric matrices, not real, but complex symmetric matrices in a neighborhood of 0. So this is a local conjecture, all right? So then there exists complex orthogonal matrices U and V such that this is true. So as I said, I emphasize this is a local behavior conjecture. All right. And you can also interpret it as kind of the sum of two elements in two orbits under certain action. And this is the 2x2 case. Not that they just conjecture it without anything. They establish the conjecture when n is 2. And they also use the 2x2 as an example to show that the statement is false if the symmetric matrices S and T are too far away from the origin. So that's why the conjecture is a local conjecture. All right. So, and I myself have a conjecture. Suppose S and T are n by n compact symmetric matrices, then there exists unitary matrices U and V such that we have this formula. All right. But notice that, oh, sorry, this conjecture is a global behavior conjecture. All right. I don't require S and T to be close to the zero matrix. All right. But here the difference is I need unitary matrices. And over there, they want complex orthogonal matrices. All right. So that's the major difference. So this is unitary here. Okay. All right. And I believe it is true, but I don't have a proof of that. All right. So, and this is the two, as I mentioned, when I established the result with my two former PhD students, this is the major result that we make use of it. All right. It's in the context of differential geometry and algebraic geometry. I don't want to get into the detail of that. So this finished my discussion. Thank you very much for your attention. Any question?
Thank you very much, GY.
Oh, thank you.
I have a quick question. So what happens if the conjecture is true? So
which conjecture? My conjecture?
Okay, yeah. For example, this your conjecture, the last one. So what could we get from that?
It reveals a little bit more about the structure of matrix exponential product. You can see it here. Okay, look at that. ET, if T is a complex symmetric matrix, right? And then you have that, and then you have that, right? And then multiply them together, right? So it must be something, right? And that something is the exponential of that. And look at the left side. It is from S and T. So then there should be, I can't say must be, there should be some relation, right, related to S and T, right? And if you insist, oh, I want to express as exponential of some matrix, and that some matrix should have some relation, right, with S and T. And this formula reveal, if it is true, reveal the relationship. Okay.
I feel like this is very strong, if that is true, because you remember the Archimedes theorem inequality for trace and singular values, eigenvalues.
Yes.
Modularizations. So there's something like, related to this. When
yeah. I don't know. I worked on it for more than 2 weeks last year, but I couldn't get it proof. Okay.
I have a question. For this conjecture for the case of real symmetric matrices, it was solved by your paper in 2021, right?
You mean this conjecture here?
Yeah, this conjecture, not for complex symmetric matrices, but for real symmetric matrices.
Oh, real symmetric, yes. Real symmetric is true.
In your 2021 paper, right?
Right. Real symmetric is true. Look at that. This is
one. Yes. Okay.
This is true. And as you know, SON is part of UN, right? So, okay.
Right.
But now you expand it to complex symmetric matrices. And of course, you cannot limit yourself to SON. My question is, if you expand it to unitary matrices, would the formula be true? Okay. I believe it is. I strongly believe it is true, but I don't have a proof.
And what is the key point that make the real case easier than the complex case?
Because we have this theorem. All right, so we have this theorem, and SLNR is a simple Lie algebra, and then we can do it. But here we don't have the parallel for the second one. We don't have the parallel here, right? So, yeah, that's the problem. Now you can use some identification. I try to, but there is some sort of difficulty I need to handle it. I was not able to do it.
Would you please show me? Go ahead, Till.
Yeah. So it seems that if you want to attack the conjecture for complex symmetry matrices, then it seems that we have to come back to the decomposition of the Lie group, special linear Lie group, add a decomposition of sums of sorry, in the real case, you have a decomposition of special linear group to the sum of something, two different things. And it seems that if you want to solve the conjecture for complex cases, then we have to do a similar way, right?
I hope there is a similar way, but I don't see it myself. It might not fit into the Lie setting very well here for the compact symmetric matrices. Yeah. But if you have some idea, you're welcome to communicate with me. I would like to see it being resolved. Either the global conjecture or the local conjecture. This is the local conjecture. Okay.
Yeah. Interesting.
Right. And I think So and Thompson also used perturbation theory to handle the 2x2 case. Okay.
Okay, I feel, remember the Golden-Thomson inequality for trace?
Yes.
So
it's a very nice inequality, Golden-Thomson inequality.
So if suppose that it is true, right? So we take the trace of both sides. So you get trace of e to s times e to t equal trace of e to, this linear combination.
Right.
And that is less than, it is greater than or equal to e. Trace of e to
because
s
you can
plus
use
t.
this move. I know what you mean. You want to take trace on both sides, right?
Yeah.
So you move this term to the right side, and then you have e or this to the right side. So you have es, et, and you take trace, right?
Yes.
And then the right hand side would be the trace of this guy, and the trace of this guy would be the exponential of the determinant of the sum. Okay.
So if you apply the Golden-Thomson inequality, it turns out that, like we suppose that the conjecture is true, right? True. Then you get some inequality between UST trace of UST transpose, V transpose, and trace of S plus T. So it's surprising.
Yes, but you don't know U and V. You don't know how to construct U and V. You only know they exist.
Yeah.
You're right. I mean, if you combine Golden-Thomson inequality, you get something, but it relies on U and V. Right? There could be many U, there could be many V.
Okay.
You make a very good point. Yeah, Golden-Thomson inequality is very important in physics, I believe.
Yes, in
statistical mechanic.
Yeah. Thank you. So do we have anything?
I would like to mention quick historical question.
Has been extended also in the context of Lie theory as well.
I see.
Yeah.
I have a quick historical question. In the original paper by Litsky in functional analysis and application, so the formula was there, but there was no proof, right?
Right.
And then Thomson, he just proved the existence of U and V, but there was no explicit way to construct them. Is that the case?
Yes. First, Lipsky, this is the paper.
Right. Yeah, functional analysis and application. Yeah.
Right. it's on, as you can see, only 2 pages.
Yep.
Okay, only 2 pages.
But that's what quite common back then. Yeah.
Right. Yeah, I know this is quite common thing in Russian culture, in the mathematical community. Not true.
Even though it's kind of weird, because I know this journal, they do accept longer papers. I mean, if it was declared, there was a limitation of 6 pages or whatnot. I guess there was a purpose of that, of just announcing the result.
Yeah. As a matter of fact, I myself communicate with Bob Thompson. Before he passed away, he told me, I think in the 80s, he told me that, yeah, there is no detailed proof given by Lipsky. He tried to communicate with Lipsky, but no reply.
Yeah.
He did. I mean, I think at that time he wrote a letter, no email at that time, but no response.
So when was the first constructive proof of those orbits of U and V? Where did it appear first as not just the existence results, but rather?
Oh, the first proof was non-constructive.
What existential?
This is the paper.
Klitschko. Okay.
Costco. Yeah.
Right. Got it.
I think he migrated from Russia to Turkey in the 80s or 90s.
Rather 90s, yeah.
90s, yeah. After the Berlin Wall.
Okay. All right. Thank you.
All right. Thank you very much.
Yeah. So if we don't have anything else for our speaker, let's thank our speaker again for his interesting talk.
Yeah. Excellent, clear talk. Thank you.
Yeah. Very clear.
Thank you.
Thank you very much.
Thank you, TY.
Bye-bye.
Yeah, bye-bye. You have a good day.
You too, everybody.
Thank you, Dr.
Thank you for coming to my talk.
Sergey, would you please stop recording?